There we go. Okay, so that's where we were last time. We learned about propositional functions and the quantifier for every. And today we're going to finish up the section by talking about the second quantifier. And we're still going to be talking about propositional functions today. And we need a domain of discourse, things that can be plugged in to our function. It's going to be capital D. So the next one, the next kind of propositional function is there exists. I said propositional function. The next kind of quantifier is there exists. And the name of this one has to do with the exists part. These are called existential or existentially quantified statements. So these simply assert that there is something, something exists. That's why we use this word existential, not referring to existentialism or any sort of abstract philosophical kind of thing. Just asserts the existence of some object or some idea or something. So last time we had the symbol upside down A, and it sort of meant all, for all. This one we're going to have the symbol backwards E for exists, or there exists. So instead of writing out this in words, there exists X such that P of X, instead we'll usually use the symbols, the new backwards E, and then X, and then the propositional function with X plugged in. And the way you would read this in English is exactly this. There exists X such that P of X. Where P of X is going to be some proposition. So it would make sense in context. It would finish the sentence. So since this quantifier is asserting that something exists, that means it's only true if P of X is actually true for at least one X. So there exists something. That means it has to be true at least once. And I should specify, since we already named our domain of discourse, 1x in D. And this is going to be false if that doesn't happen. So if there isn't at least one that's true, 1x that makes this propositional function true, then that means it's always false. So it's false if P of X is false for all X in our domain of discourse. Any questions over the definition? Okay, so let's see if we can verify one of these existentially quantified statements. And it's a good idea to always translate these, at least mentally, into English. This one says that there exists, let's see, someone's microphone just turned on. Are you trying to ask a question? Or were you just logging in? Okay, so this one, I haven't said what the domain of discourse is. What do you think that should be? The domain of discourse for this equation. What kinds of things can you plug in?
Integers.
Integers. Could you plug in fractions? Oh, and yes, Davian just gave the answer. We can plug in fractions or square roots or anything like that. So it is all real numbers. So if we wanted to translate this into English, we would say there exists a real number x such that this equation is true. So this is how you might translate the symbols, the symbolic argument, into words that are, actually understandable by us. No. So in order to verify the statement, we have to make sure we understand what the statement is saying. So far, we've just made sure that we understand what it means. And in order to verify the statement, we have to show that there is a solution to this equation, that there's actually a number where this works. William, so your idea is to plug in real numbers. Yes, it is possible to guess the correct answer. And this one is definitely guessable. But in practice, there's way too many real numbers for us to plug in all of them. If we weren't, able to guess really quickly, that could take a long time. So the other way is to actually do algebra. Right, we only need one solution. So if you can guess one solution, then you're done. The other method is to use algebra and actually solve. Yeah, so that is the answer. So this one is actually relatively easy to guess, even though it looks pretty hard. So you have this fraction on the left and this other fraction on the right. And you see x is on top over here, 2 is on top over there. So if you guess x equals 2, so that it matches this, you will get the correct answer. So this would give you 2 over 2 squared plus 1. So that's 4 plus 1 in the denominator. or 2/5. Good. And like I said, the other way is algebra. And maybe I can just do the first couple steps to show you what you might have to do. We like to get rid of fractions as soon as possible. So what you would want to do is, I guess, what you call cross multiply. That's what most people call this. Oops. You clear the denominators. So you would say 5x is equal to 2 times that denominator, x squared plus 1. And then you would have to multiply out and then solve the polynomial, solve the quadratic.
So if we have to verify, we have to actually find x in that case.
Right. So if you want to verify an existential statement, you have to show that it's actually true. There is actually some x that you can plug in. So you have to find it. So if you weren't able to guess, this other method using algebra would definitely work. It means solve in situations like this where you have an equation, where you're saying a solution exists, then you have to find that solution. But there are different kinds of existential statements. Like, just to make one up real quick, there exists x, well, maybe I'll just write it out in English. Maybe there exists a planet with life on it. Okay, so this is an example of something that's not really math. It just says that there exists a planet with life, and we know that this is true because, well, we live on a planet and we're alive. Okay? So you don't actually have to solve anything for that one. Any other questions before I flip over to the next page? Okay, so this next example involving existential quantifiers is a bit different because we are trying to show that it's false instead of true. And remember that an existential statement is false if it's false for every single x that you plug in. So that's what we have to show for this problem. So we have to show that this is always false. So just translating it into something that we can do. Using math. So what is the negation of this inequality? What does it mean for this to be false?
1 over x squared plus 1 has to be greater than 1 all the time.
Well, that's what this That's
I
when
mean,
this is true.
less than 1 all the time. Sorry.
Okay, good. You're really close. So we have to show that 1 over x squared plus 1 is less than, actually, or equal to 1. For every x. Because if it was actually equal to 1, then this strict inequality would be false still. So it could be equal. So in order to show that this statement is false, we have to show that this inequality is true. So we've sort of swapped around our way of thinking. So instead of showing that this is, when we're asked to prove that something is false, we have to use the negation. That's kind of right. Let's see, what's the best way to answer that? If you're wanting to show that something is false, then you're showing that the negation is true. So remember, if P is false, then not P is true. So this is the kind of thinking that we're doing here. So it's kind of hard to show that an equation is false, but it's easy, or at least easy in the sense that we know how to do it. It's easy to show that an equation or inequality is true. We just have to solve it or work through some way. And this one, I'm just going to work from first principles that we already know. We know that x squared, is greater than or equal to 0 for any real number. This is something that we talked about last time, right? If you plug in a positive number, you'll get back something positive. If you plug in a negative number, two negatives multiplied together give you a positive. So this always works. And, well, I can do things to an inequality, like I can add 1 to both sides. And the inequality is still true. So that means x squared plus 1 is greater than or equal to 1. And I can also divide through, as long as I'm not dividing by 0, and as long as we don't divide by a negative number, and we have to, change around the direction of the inequality, we can divide. I'm going to divide by the left side. Divide by x squared plus 1. That's definitely positive, and it's definitely not 0. So that's allowed. What do you get? This cancels on the left. I don't want to switch around the direction yet. Try that again over here. So we get a 1 on the left. And on the right, we have 1 over x squared plus 1. And that's exactly what we were trying to show. It's written in the opposite order, you can see, but it's the same thing. We were trying to show that this is always true. We've done that in order to show that this is always false. or that this existentially quantified statement is false. Okay, so any questions? Okay, so this kind of backwards way of thinking that we were doing here, I need to summarize. And these are called De Morgan's laws for logic because they're closely related to the other De Morgan's laws that we already know. And it says, these laws say that the following pairs of propositions have the same truth values, so they're equivalent propositions. So the first one says that the negation of this statement for every x, p of x, it says that this is equivalent to changing the universal quantifier, the all, upside down a, to an existential quantifier, an e, and then I put the negation on p instead. So you can think how this is related to the other De Morgan's laws. I can just write one of them over here in case you've forgotten. So they tell us how to distribute negations. We flip the symbol and put negations on the other pieces. Like so. So we're flipping the A to an E and then distributing the negation inside. Let's see. So going back a little bit earlier, we've already talked about what it means. This is the universal there for every statement. We already talked about what it means for this to be false. We know that this is false if p of x is false for at least one value of x. So another way of saying that p of x is false for at least one value of x is to say that there exists, using the other existential quantifier, there exists a value of x where not p is true. So just rearranging the sentence a little bit. And that's how we get this first law here. And then there's a similar law for the existential quantifier. So here we have a negation symbol on there exists an x such that p of x. And you might be able to guess that it works the same way, just like De Morgan's laws work the same way. You will switch the e to an a, or the backwards e to an upside down a, and then distribute the negation symbol inside. Going back to the previous page again, we've already talked about what it means for this to be false, for there exists an x such that p of x to be false. Remember, it's false if p of x is false for every x, for all x in the domain of discourse. So another way of saying that is that not p of x is true for all x in the domain. And that's what this law is telling us. So for all, or for every x in the domain of discourse, the negation of P is true. Are there any questions over that? Okay, so let's try out this idea on a few simple statements like this one. I want to write the proposition, every gamer loves Call of Duty symbolically, and then I also want to find its negation symbolically and in words. And the thing to do when you have these things with existential quantifiers and propositional functions is to make sure you identify them. Here, the propositional function, the P of X, is saying that X loves Call of Duty. And then the domain of discourse would be the set of all gamers. So if X means that and our domain is the set of all gamers, that means we can rewrite this statement that says something about every gamer as a universally quantified statement. So in backwards A, upside down A, and then X from the set of gamers, and then P of X for X loves Call of Duty. Okay, so this is the statement that we're looking at, and we want to find its negation next. So you can just put a not symbol on the outside. And what we're going to want to do is replace that with this form from the first De Morgan's law. So this is the same thing. It's logically equivalent to switching the A to an E and then putting the negation symbol on P. Okay, so we've translated this to a symbolic argument. We found the negation symbolically. Now we just want to translate that into words. Does anyone want to try this one? Try saying this in words with this filled in.
The negation.
Right, the negation. Right, there exists a gamer that doesn't like Call of Duty. Right, and that's a true statement because you don't. Good. Okay, any questions over that one? Okay, so let's try this next example then. We want to do the same thing, rewrite this proposition symbolically, and then find its negation using symbols and words. So this one, the proposition says some birds cannot fly, and that's definitely true. Penguins, emus, ostriches, for example. But how would we write this symbolically? Well, let's think. This says a bird cannot fly. So
You want to use the true statement, right?
right. So since this is a negation, we want to think about the true version of that. So if the negation is cannot, then the true version is can. Or the non-negated version, let's say. So it would be X can fly. And then our domain of discourse should be the set of birds. And this sentence includes a negation, so it's going to have a not P of X. And this is a universally, not universally, excuse me, this is a quantified statement. Is it a universal or an existential? So should I put an AX or an EX? E, right, so it says some birds cannot fly, so at least one bird can't fly. It's not saying that all birds cannot fly. Good. So the negation we'll put a not symbol on the outside. Okay, lots of parentheses on this one to keep things organized. And what we'll want to do is move that negation from the outside to the inside using the second of De Morgan's laws. So the existential becomes a universal. And then we have a negation of what we find on the inside. It's one too many. Or maybe, yeah, that's good. So we have a negation of a negation. What happens? Does anything happen when you have two not symbols? They cancel, right, a double negative. Just like when you have two negatives in math, two negations cancel. So we're actually saying for all x, P of x is true. Good. So that's how that simplifies. And we just need to translate this back into words. Someone want to give that a try? Right, all birds can fly. That's exactly it. Any questions over that example? Okay. So there's one more thing I want to do before we can move on to some of your questions. What I want to do is write some pseudocode for a program that determines if an existentially quantified statement is true or false. And I need to give you the domain of discourse. It needs to be a finite set since we're talking about computing. And I'll just stick with
announcing.
Stick with Okay, we'll stick with the notation that we used last time for our pseudocode for the universal quantifier. So our sets D1 through Dn. Any ideas? So when should our program return true? And when should it return false? Anyone want to give that a try? We don't know. We don't know what the actual function is. We just want to think of it as some function, some propositional function. So maybe we're trying to write a program where we can plug it in. So X has to be in the domain. Okay, good. So we're definitely plugging in things from here. X has to be in the domain. For a loop that rolls through the domain. Okay, good. So we need to somehow cycle through all of these elements. There's, I guess, several ways that you could do that. But if we're just speaking in words, maybe just say for I from 1 to n. And then that'll let us choose each of these in sequence. Okay. And what should we do with that for loop? Okay, so we need to see if P is true. And remember, we're plugging in D, I. So D with a little subscript I, starting at 1, and then 2, 3, 4, 5, all the way up to n. So if this is true, what needs to happen? If one of our statements is true. Good. So if at least one of these is true, then our program should return true. Okay, so this for loop is going to cycle through our domain, plug all of them into the propositional function, and then it's going to return true the first time it detects a true statement from the propositional function. So what if this never is true? What needs to happen? Good. So you can put your return false. I guess you could use an else statement, or you can actually just go outside of the for loop. So if you make it all the way through the for loop and you never get to the return, the end function line, if you never run that, then you'll get down to the end and then return false. Good. Yeah, that'll work. Let's see. So at the beginning of class, there was at least one question that I said we would get to at the end from section 1.4. So what was that question? Let's see, who asked it? Davian, what was your question? Number 34. Okay, so that's here. You're trying to show that addition is valid, and it says to make sure to refer to table 1.4.1. So you turn back and you find the table. And this is the list of the rules of inference. And we're going to look at the addition rule. So let me write that down on my paper so we can actually do some work. Okay, so what we're trying to do is show that we can add on an extra proposition using an or, and we get a valid argument. So we have to remind ourselves what valid means. And this is a very specific word when we're talking about logic. It says, or it means that if the hypotheses are true, then the conclusion has to also be true. So if you're trying to show that an argument is valid, the best way is to make a truth table. And you want to make sure you have columns for each of the hypotheses and another column for the conclusion. And we'll have two simple propositions P and Q. And we need a column for our hypothesis and another column for the conclusion. This is a short argument, so there's not much to put in. So there's the hypothesis, there's the conclusion. So what we're trying to see is that every time we have a true in the column for the hypothesis, we also have a true in the conclusion. And we have about a minute to fill this out. Let's see if we can do it. So start by filling in the combinations, the 4 possible combinations of truth values for your 2 propositions. The hypothesis is simply the first column, so you can copy that over. And then the conclusion, P or Q, is true if at least one of these 2 arguments is true. So we have to go back over here. Here we have 2 truths. Here we have 1 true. That one also has 1 true. And then we have 0 truths, 2 falses. So now we have to find the rows where the hypotheses are true. The first 2. And then we have to look at the conclusion and make sure that the conclusion is always true whenever the hypothesis is true. So does that check out? Does that work? Yeah. So that one's good. And most of the problems in this section are similar. You're trying to determine if an argument is valid or not. And a lot of the time you'll make a truth table like this. And we went over a few different ways. You can use rules of inference sometimes, and sometimes you can guess a combination of trues and falses that makes it invalid.